There we go. Yeah, okay, questions? Yeah.
I don't understand the first problem on the exam. Like the ratio.
Oh, the ratio of the resistors?
Yeah, like I compared it to 1 and then it was wrong.
Yeah, okay, okay. To be continued here. Let's see here. Okay. Thinking about resistors for a second. And I don't remember the specifics of the problem, but I can
Plug it in and got the resistance and then it turned out to be wrong.
But it was like you stretch it, right? You take the wire and you stretch it, or was it that you cut it? Okay. Oh, okay, I'll have to go back and look at it, but the underlying idea about it is, okay, what happens to the resistance of a material if you make the material longer? Or if you make a wire longer, say if I start off a wire like this and I stretch it, what happens to the resistance? It increases, right? If I stretch the length of the wire, it goes up. Next question. So, I mean, you know that the resistance is proportional to the length of the wire. The second one is, how about the area? If I take the area of a wire and I shrink it down, what happens to the resistance? If I decrease the area, the resistance goes, okay, so you got the basic idea, right? As I make the wire longer, the resistance goes up. As I make the area of the wire smaller, the resistance also goes up. Good so far? Now, I have to go back and look at the specific wording because I don't remember for sure. But let's say for a second, I start off with a wire and I stretch it. We've already talked about, I certainly increase the length of the wire. What happens to the area of the wire as I stretch it? Is it going to get thicker or is it going to get thinner? If I take that wire and I stretch it, it's going to get thinner, right? We can always try this, right? Take some bubble gum. There's our wire. If I stretch the bubble gum, as I make it longer, it inherently gets thinner. Right? Now I have to double check. I don't know if this is exactly how I phrased it, but one of where my mind immediately went to was, shoot, is there a good way for us to gauge by how much the area changes? Did I give you numbers for the area and the radii? I don't remember for sure.
Yeah, you gave us like ratios for all of them. So.
Oh, okay. So I said the D increases by this much, the area. Okay. So I don't have to, because what I was thinking of is, okay, constant volume, and then you could find the ratio of the areas that way. Okay, no. So that I think you've got everything that you need. The idea is, maybe the idea is that, I think I said R1 over R2. So R1 over R2 would be something like, okay, so we have the idea that the distance goes up, the resistance goes up. The area goes down, the resistance goes up. So we have something like this, rho D over A. And I'll say that's for the first, and you could divide that by rho D2 over A2. And then we just say, oh, goody, there's some cancellation. The material that I make doesn't matter because the material the resistors are made out of doesn't matter because I'm dealing with ratios. And so if I get rid of the compound fraction, we end up with something like, D1 over D2 times A2 over A1. And those are the ratios that I gave you, correct? I gave you the ratio of the distances, I gave you the ratio of the areas. So that was the idea I was testing you on is essentially, do you know how the resistance depends on the distance in the areas, the cross-sectional areas?
I studied for like 20 hours and I still only got like 25% from the multiple choice.
Well, let me look at it. So truth be told, I was grading my astronomy exams. I haven't looked at your guys' exam yet. So give me some time to actually look at it and see if there's any. I mean, the other question is, okay, is there some sort of, it's not beyond me to code an error. So let me double check to make sure that there's problems if there's a problem that everybody got wrong, that indicates something to me that I either asked an unfair question or put a coding error in. So give me an afternoon to look at stuff and see if I can start grading and see what it is. The other one is I think I heavily weighed I want to say that I heavily weighed the handwritten stuff, didn't I? It's like I think the multiple choice is only like 25% of the overall grade, if I recall correctly. So let me also look at that. So yeah. Other questions? So this is just another cutesy demo of what's called magnetic field or magnetic domains. So we're talking about how do you actually create a magnet, and the idea is simply you just try to get as alignment of the atoms. Okay. What this does is this is just a macroscopic demonstration of that idea. So you can take each of these compass needles represents an individual atom, and you can, mix them up using some external magnetic field, and they will naturally form what are called domains, little patches of alignment throughout the entire material. Okay. So then the issue is that when you want to create a stronger magnet, what you do is you try to get more of those, you try to make the domains larger. You try to get more of those tiny magnets all aligned in the same direction. And the larger the domain is, the stronger the magnet is at the end of the day. So yeah, okay, they jostle it. You can see that nearby atoms start getting into an alignment. And I think they jostle it again. Do you do the whole thing? Yeah. Let's pause it right there. Pause. So you can see like these compasses are all basically in the same direction. These compasses are all in the same direction, and then you've got some small ones. I found that cutesy little video and I said, oh, that's nice. I should do that too.
Does it depend on like how long you keep the magnet in a certain place?
I'm sorry?
Does it depend on like how long you keep the magnet in a certain place?
Let's see here. I'm sure that if he kept the magnet at one location, that would certainly entice a particular domain to be larger. So I think yeah, I'm sure it would. Mm-hmm. Yeah. Microscopic, again, that's a macroscopic demonstration, but you have microscopic. Let me turn off the lights here to get a better contrast. So on this left-hand image, what you're looking at is not optical light. There we go, those two. Each of these little difference in colors is due to the orientation of the magnetic field in that particular domain. So this little patchwork is indicating different directions for the magnetic field in each of those little pieces. And again, to make the magnet stronger, you just want to make those domains as large as possible. So it gives you microns. 20 microns, ballpark. I want to say 50 microns is about the width of a human hair, if I recall correctly. Double check me on that, but 20 micron is 10 to the negative 6 meters. So I want to say about 50 microns is the width of a human hair. So these are about half the width of a human hair, just in terms of those domain sizes. You can also do something like this. This is one of those domains, and it's an image, or it's a JPEG, or a GIF, or whatever. Again, the color is just indicating the magnetic field directions. And so as you notice this magnetic field, there's an external magnetic field being applied so that the domain slowly grows and grows and grows until it takes up pretty much the entire image.
So does the direction that the atom facing reflect light in different ways?
Yeah, I'd have to go back and look at this, but yes, it's something like that. I don't know if they're using optical light or if they're using radio waves. I don't know what type of electromagnetic spectrum they're using, but yes, that's the idea, is that you get a different sort of interaction based on the direction that of the magnetic field.
Like emit a photon in different direction or something.
You know, I'd have to double check. It might have something to do with the polarization of the light, but I have to go. I shamelessly stole this from Wikipedia, but I didn't go into very much detail about how the image was generated. I'd have to go and look it up. Yeah, did I shamelessly? Yeah, I shamelessly stole this one from Wikipedia. So yeah, I'd have to go back and look at the paper. But my recollection is it's either the type of light or the polarization of the light, and I don't remember which. Or both. Could be both.
What does it mean to light to be polarized?
Shoot. Okay, let me think about this. We haven't gotten there yet. I know I've name dropped it a couple times, so yell at me if this doesn't make any sense. The reason we call light an electromagnetic wave is because we think of light as being a changing electric and magnetic field tied together. So they call it the electromagnetic spectrum because light is literally the changing of an electric and magnetic field simultaneously. Is that okay? I mean, we have to still discuss it a little bit more, but that's basically what light is. To say light is polarized means that the electric field is all in the same direction for all of the light. So a polarized beam of light means that every beam of light that's coming from that light source has the electric field in the same orientation. That's what it means to be polarized. Now, the easy way to do that is to take some light source that is not polarized and run it through what we call a polarizer. And then the light that comes through is automatically polarized. In fact, this is really nice. Most sunglasses are made like this. Thank goodness it doesn't block all of the light. Otherwise, those sunglasses would be not very effective. Well, I mean, it would be too effective. So what polarized sunglasses do is that it's taking the unpolarized light from the sun, and it's blocking all of the light except for ones that have a particular orientation of the electric field. And those are the ones that come through the lens. Which is also why polarized sunglasses dim the light. By exactly half, turns out. That's a different issue. But that's what it means. Polarization just means the electric field of the beam of light is in the same orientation. Other questions? And we'll have to see if we actually get to that or not.
The direction of the magnetic field related to the direction of the electric field?
Perpendicular. Yeah, good question. Yeah, so the electric field, if the electric field is up and down, the magnetic field is left and right. And incidentally, the electric field is up and down, the magnetic field is left and right, and the light will travel in the third direction. So, up, down for electric field, left, right for magnetic field, and the propagation of the wave is that way. Shoot, what is that called? It's a transverse wave. Yeah. So water waves, transverse. The direction that the water travels is perpendicular to the direction that the wave travels. The water goes up and down, the wave travels forwards. So that's called a transverse wave. Let's see, what's a longitudinal wave? Sound is a longitudinal wave. Sound waves, you could think of it as being push-pull, which is in the same direction that the wave propagates. So a sound wave is push-pull, like pressure waves that are in the same direction that the wave propagates. And so we call those a longitudinal wave. So transverse, the medium is perpendicular to the direction of travel. Longitudinal, the medium is parallel to the direction of travel. So light is a transverse wave. The electric field goes up and down. The magnetic field goes left and right, perpendicular, and the wave travels in the third direction. No, that's a really good question. Which is why, if you ever, sorry, this is a bit off topic, but that's okay. If you ever look at a conceptualization of light, you'll see probably something like this. I don't know if I can draw this very well, but usually you see like a sine wave. They use, what that's supposed to represent is the electric field. The strength of the electric field at different locations in space. But then sometimes what you'll see on top of that is the magnetic, sometimes they'll draw the magnetic field as well. So red is the electric field. Then they'll have the magnetic field going something like this, where now it's inside in the page and then it's back out of the page. So it's like left and right. And then they usually draw something like, oh, okay, well, the speed of the wave is traveling in this direction. Sorry, that's a terrible drawing, and I can't do any better right now. Yeah, you don't have to agree with me. You're supposed to be like, Greg, you're the next Picasso. It's my blue period, okay? Yeah. Other questions? I'm going to cut off my ear. That'll make me more motivated, right? Favorite painting? Did you guys have like, what's your favorite painting? Anyway, I'm just curious. Favorite artist? This is completely unphysics related, but. Favorite museum? Come on, you gotta have something.
My mom's favorite thing.
Okay, so your favorite artist is your mom?
Yeah.
Okay, we'll take it. I mean, you guys gotta get out more. I mean, I know we're not exactly in the art capital of the world, but you gotta go out. Well, if you ever find yourself in the Chicago Museum of Art, my personal favorite is Un dimanche sur l'île de la Grande Jatte. It's a Sunday afternoon on the island of Grand Jatte, or Jatte, J-A-T-T-E, something like that. So if you ever get to the Chicago Museum of Art, it's by Seurat, and it's a style called pointillism. So basically, instead of painting with brush strokes, he paints with dots.
So that's Sunday afternoon.
Yeah, Sunday afternoon in the park, yeah. So, and it's really interesting because it takes up like the side of this wall, like from the door to the pillar. It's about that size. And the idea is that, oh, this comes into, optics. Oh, shoot, I should save this. But the idea is he paints with dots of color. And the only way to get a blend, and he paints in pure colors, so he doesn't mix the colors on his palette. Rather, he places two dots close to each other, and if you view it from far enough away, your eye blurs the two colors together to give you a perceived third color. So this tableau, the painting is about the size of the wall, but it's meant to be viewed not from this close where you can see the individual dots, but it's meant to be viewed from about 15 to 20 feet away, where your eye can no longer perceive the individual dots and it blends the colors together. No? Wait, don't tell me you're a fan of haystacks. Haystacks? Series of haystacks drawn by Monet? No? Yeah, he like drew haystacks in a field at different times of the day, so he's playing with the play of light on the haystacks. So, like the impression. So like you look at one, it's kind of blue, and it's like, oh, early morning, and then you see one that's golden, it's like late afternoon. Yeah. Okay. Huh? Liechtenstein?
Yeah.
I'm not familiar with that one.
He's like comic book type stuff.
Oh, okay. Okay, so more like Warhol kind of pop.
Yeah.
Okay. I mean, I gotta say that Banksy, I love Banksy stuff. You ever heard of Banksy? Yeah, he's like a street artist, like a kind of a tagger. Like the last one I remember was that he had a painting for sale at auction at Christie's, and somebody might have known about this. I don't know for sure. So when the painting sold, he had it in a frame. It was in a frame that was also furnished by Banksy. And when the painting sold, somebody in the audience, and they don't know who it was, had a remote control for the frame. And unbeknownst to people at the auction, there was a shredder in the bottom of the frame. So once it sold at auction, there was somebody in the crowd that activated the shredder via remote control, and it literally shredded this painting after it was bought. Which probably made it worth more. No, you haven't heard of this? He's the guy that like he set up a shop in Paris, like on the banks of the Seine, you know, like those $20 like cheapo painting shops on the banks of the Seine. Okay, and he was selling his paintings for 20 euro. He spent the entire day. This is a well-known street artist. I mean, nobody knows who he is, like what he looks like, but his material is really well known. So he was selling his paintings, original works of art, for like 20 euro. He managed to sell 2 the entire day, something like that. You know how much those paintings were worth? Like 20 to 30K each. He sold 2 of them as a street vendor. So it's like really weird. Like, I think he's the guy that he had an exhibition, and the theory has it that he actually broke into his own exhibition and stole one of his own paintings. No, you've never heard of Banksy?
I think people would rip like when he would do like art on the streets, they would like carve the like paintings out the like walls or whatever. He wouldn't sell them. So I think like I don't know what really happened, but I think people used to
Yeah, exactly. Like people would take the wall, like when he tagged something, they would cut the wall out and sell the wall. Like just really weird. Anyway, okay. Yeah, get out. Find art, find something you like. Okay. That's all I have to say about magnetic fields, about magnetic domains. You know, we'll leave that behind. So we're going to break into a slightly different topic. We're still staying with magnetic fields. And this one can get a little bit finagly. We'll call it finagly. But it's an empirical result, and it's really important because it serves as the basis of pretty much all of our electrical generation. So it's so stinking important that I've managed to skip over a couple of related topics that I said, okay, that's not worth our time. This is the one that I said, okay, we can't really skip over it. It seems really important. And it's known as Faraday's law. So here I've got just a brief demonstration, but here's the interesting thing about Faraday's law. So you notice I have a coil of wire, and I've attached it to the ammeter. Now I've got a bar magnet, coil of wire, bar magnet, and you notice what's going on right up here. What happened? And it's, oh, let's do it again. Can I play it again? No, I cannot. Yes, I can. There we go. Right, coil of wire, take a bar magnet. There's a bar magnet. I pass the bar magnet through the coil of wire. And what do you notice? You notice there's a current. Right? We've already talked about how moving charges can generate magnetic fields. Faraday's law goes the other way. Faraday says, well, if moving charges can generate magnetic fields, maybe moving magnetic fields can generate moving charges. And indeed, that's exactly what's going on here. If I take a magnetic field and I move it, so that's me moving the magnet, I'm changing the magnetic field, I can actually drive a current. And you notice as I put it in, the current's going one way, as I pull the field out, it goes the other. So that you notice the needle bounces just a little bit. And it's going back and forth. And that's the basis of Faraday's law. Faraday basically comes in and says, if currents can generate magnetic fields, maybe magnetic fields can generate currents. So we have to get into that. That's the thing that we're going to get into. Of course, another demo is this. This one's always lovely. Of course, if you've seen this, don't tell your friends. All right? So here's another really interesting demo that's also the same idea. I've got two pipes, same length. Always fun. So I've got two magnets. All right? Ready for this? Oh, I should do it on the table so you can actually see. Ah, there we go. So no tricks. Ready? Your mark. Get set. Go. Oh, it's magic. Oh, right? Let's do that again. Could probably sing a song while we do it, right? No jokes, right? Ready, set, go. Oh, it's called timing shut out. Weird, right? What's even more weird? What's that made out of? Copper. And copper is not magnetic. Right? Now stick. Come on, stick. No. So that's weird. Right? I mean, your initial impression is, oh, Greg's just using magnetic material. That's why the magnet, I'm guessing. I'm guessing you say something like, oh, well, the reason the magnet falls slower in this is because it's magnetic material. And I agree. If I use the steel pipe and I drop the magnet in, the magnet's going to stick to the wall, and that's it. It's not going to fall. But I didn't use a steel pipe. I used a copper pipe, and copper isn't magnetic. But yet you saw something going on here. So the question is, what's going on there? How do we describe this behavior? And what's the difference between these two? I mean, they're both not magnetic. So why does the magnet fall slower in this one than this one? What's the defining characteristic that causes the magnet to fall slower in this pipe than this pipe? I'm sorry? Oh man, I don't know what that means. I mean, I know you're talking like the orbital of chemistry, but okay, we'll go deeper than that. But I assume that has probably something to do with it. One's a conductor and one's an insulator, which I assume has something to do with the d orbitals. Namely, when you put it into a crystalline structure, you have those shared decentralized or delocalized electrons.
Like metals is described as like an electron seed.
Yeah,
They're like freely.
yeah, you got the conduction band. Yeah, you're right. So it comes back into, yes, conductors versus insulators. The fact that there is a conduction band here means that when the changing magnetic field occurs, that drives current in the conductor. Whereas the insulator, it doesn't drive very much current. Right? By definition, an insulator does not allow charges to easily flow. Whereas a copper pipe allows charges to flow easily. Now we could go a step further. Qualitatively, you can tell me exactly why now. If a change in magnetic field drives a current in the copper, what can you tell me about the current, how would I say this? So the changing magnetic field drives a current in the sucker. But that current that's driven in this thing generates a magnetic field. The falling magnet induces a current in the copper. The induced current in the copper generates its own magnetic field, right? Moving charges generate a magnetic field. And what can you tell me about the direction? Let's say that this is the North Pole that I'm dropping in. What can you tell me about the direction of the magnetic field in this copper pipe? Is it opposing the magnet or is it with the magnet? It's opposing, which means the magnet falls slowly. Right? If it were going with the magnet should go faster down the tube. You observe that it goes slower. And again, that's just qualitative. We'll have to go through and work through more of that. And so we'll go through that whole thought process again at some point. Okay? Well, you have another idea. Copper, you got an idea. I mean, if I got a 6 foot, I think this is 6 feet. No, this isn't. I'm only 5'10", so this must be 5 feet. Okay, yeah, this is like a 5 foot copper tube. Question. If I use, say, something like, I don't know, a 5 foot aluminum tube, and I did this again. Which tube is the magnet going to get out of first? The copper one or the aluminum one? Let's say the rest of you. Aluminum, okay, I see it. Why? Why the aluminum? Why will it get out of the aluminum tube first? Because copper is a better conductor. I agree. What does that have anything to do with it? Why does that matter?
Well, better conductors and have more crack.
Okay, good. So you're using copper has a lower resistivity. Because it's a lower resistivity, it will have a larger current. Because it has a larger current, the induced magnetic field will be stronger, and therefore it will oppose the falling of the magnet.
Why does it make a magnetic field charge?
I'm sorry?
Why does it make a magnetic field instead of a charge?
Why does it make a magnetic field instead of a charge? You have asked an interesting question. Faraday goes through and says, well, if a changing magnetic field can drive a charge, maybe if a changing magnetic field can generate an electric field, drive a current. Perhaps a changing electric field can create a magnetic field. Yeah. So you say, why does it drive current instead of charge? I would argue that it is kind of driving charge. Yeah. Right, current is just moving charges. Yes.
So when you drop the magnet, which way is the current going?
Oh, that's another good question. It depends on which side of the magnet I'm using. So yes, not only does it depend on which pole of the magnet, but it also depends if the pole is moving towards or away. So I don't know for sure because I don't know which pole this is. But if I told you which pole, once we get done with Faraday's law, you can tell me which direction the current's flowing. Yep. We should do this instead of parachutes. I don't know if that wouldn't work. And it's very interesting indeed, because the magnetic force is proportional to the velocity. Do you remember terminal velocity from the coffee filter lab? And way back when, this also hits a terminal velocity. So at some point, very quickly, it's just falling at a constant rate rather than accelerating. Oh, there it is. Gotta be careful with these things. Oh, I forgot about that. Yeah, go ahead.
So why does it slow it down rather than speed it up? Because couldn't force be pointed downward? So like the magnetic force be pointed downward?
Yeah. So what ends up happening is Faraday's law. Faraday's law has a negative sign in it. Okay. So it's not, okay. Yeah. Let's see here. Bio-Savart, let me just put up Faraday's law. There we go. Put up okay, well, I'll leave it like this. The question I believe that you're asking pertains to the presence of this negative sign. Okay. That sometimes you end up with these negative signs in physics where it just is indicative of a direction, right? I chose positive x to be to the right, and when I get negative, that means that it's moving to the left. Right? Or I chose positive y to be up, and so when I end up with a negative sign, it means it's moving down. Those, for lack of a better term, I'll call those boring negative signs. Okay? Those negative signs just have to do with your choice of axes. Okay? That negative sign is something different. This negative sign is more akin to the negative signs that you see in something like Coulomb's law, or the negative sign that you get when you're talking about gravity. And what I mean by that, let me write those down. Coulomb's law, it's not very apparent, right? If I put Fc is equal to K Q1 Q2 over R squared. What does that mean? I mean, when I end up with a negative sign in Coulomb's law, what does that physically mean? Yeah, is it that they're repelling or is it that they're attracting? You got the right idea. Yeah. How do I get a negative sign in Coulomb's law? It would be attracting. I need a negative charge and a positive charge. The negative sign in Coulomb's law tells me that the charges are attracting. I would say that that's a lot more interesting than a negative sign that pops out because of the choice of axes. There is some physical meaning to that negative sign. Okay. Gravity is the same way. If you remember the force of gravity, okay. Go like this and look straight up at it. If you do something like the force of gravity, I'll put in here, you have G M1 M2 over R squared, and there was a negative sign out in front. And again, that negative sign is really important. That negative sign meant that gravity is always attractive. So those are like, more interesting negative signs. This is another one of those interesting negative signs. It's not just the choice of axes or, oh, choosing the wrong direction for current. Those are boring negative signs. This one is a more interesting one. Okay.
Probably there's delta L.
A small piece of the wire. I think maybe I left L in there. Sorry, maybe, excuse me, maybe I left this is old, this is, that was my brain reverting to something that I probably shouldn't. I think I gave it to you as mu naught over 4 pi. Did I just give it to you I times the length of the wire times, I think I gave it to you just like this. Sorry. I'll have to double check, but I think I just gave you the magnitude of the magnetic field and defined it like this. Sorry, I ran out of space there. And again, we haven't used that. That was just, hey, this is the analog expression to Coulomb's law. But what we do need to talk about is this thing. This is the fancy way of expressing Faraday's law. And we have to talk about what the notation actually means. I'll start off with the EMF. Unfortunately, EMF is a terrible historical holdover. EMF historically stood for the electromotive force. EMF, electromotive force. And sometimes you will still see it with this epsilon. Like you'll see an epsilon with a subscript MF. Sometimes it makes you think of other MFs. No, it's electromotive force. So this is back in the day, back in the 1880s or so, when the nature of the electric field, the nature of the magnetic field was still trying to be understood. And Faraday called this the EMF. He said, a changing magnetic field generates an electromotive force, causes current to move, causes charges to move, excuse me. It wasn't until later that we realized, oh, that's just a change in potential, right? A change in magnetic field causes charges to move. Well, that's like the charge is undergoing a change in potential. So more often than not, you will see these two notations interchange. I think your book calls it an EMF, but you could just as easily say, oh, a difference in potential. So a changing magnetic field will cause a difference in potential. Due to that difference of potential, charges will move. The nice thing is that if you think about it as a difference in potential, then you kind of have a way of pulling in the resistors, right? Same changing potential, because the same magnet is falling. The difference then becomes the resistivity of the material. This one has a lower resistivity, therefore current is larger. This one has a high resistivity, that means the current is smaller. So I don't know whether to apologize or not, but physicists are sometimes stupid. They keep that historical holdover. Can't do anything about it. Yes, I can rail against how silly physicists are. But I mean, chemists do the same thing, right? I think you guys still talk about beta decays or beta captures. Is that right? Beta decay, beta capture. Yeah, when you're talking about I think beta decay is an electron, or beta capture is that a proton and an electron combined to form a neutron. Why do you guys call it beta? It's just an electron. So physicists are not the only ones that are that make historical holdovers. No, am I just smoking something? I forgot, you have a fancy name for an alpha particle too, and I can't remember what that was. Like an alpha capture? I don't remember. You have an alpha decay, don't you? Yeah, an alpha decay is emitting, I think it's a helium-2 nuclei. Right, it's a +2 emission. So an alpha decay is emitting a helium particle. Well, why don't you just call it a helium decay? History, huh? Funny names are fun, yes. Okay. So that's what the left side of this is. That you could think of it as a change in potential. You'll sometimes see it named an EMF, an electromotive force. The right side is the one that we got to deal with. Big phi. A capital phi, Greek letter, not representing the angle, unfortunately. Rather, this has a very special mathematical connotation. So I better define that for you. Okay. So when you're dealing with any vector quantity, you can define what's called a flux. So a flux, and excuse me, this should be a triple equal sign. So capital phi stands for the flux, and it is defined as being qualitative. Heuristically, a flux is telling you how much of a vector passes through an area. That's kind of heuristically what it's telling you. How much of a vector, in this case, the magnetic field vector, passes through an area. You could also do something like, the flux of sunlight through a window. The window defines your area, your vector is sunlight, so that you could use that kind of terminology there. Or you could say, the flux of water through a fishing net. Or you throw a fishing net into the Ohio River, whatever you catch, just throw it back. Okay? But you could think of the flux of water through a fishing net. You use the net to define your area, and you're looking at how much water passes through. So, so that's, I don't really have any deeper thing to tell you there. That's just a mathematical idea that comes into play. What I can ask you is, based on this definition of flux, how can you change the flux of a vector field? I mean, based on this definition, what are 3 ways that you can change the flux? You can change the area, right? Instead of doing the little window in the door, you could do a huge bay window. So you could change the area. That will increase or decrease the flux. How else do you change the flux of a vector field? I'm sorry? The amount of the vector. I can change the magnitude of the vector. I can make it stronger. I can make it weaker. What's the third way that you can change the flux? Oh, yes. Okay. Now you've given it to me in order. Change B. Keep the area the same, but change the strength of the vector field. We can also keep the vector field the same, but increase the area or decrease the area. What's the third way that you can do this? Change the angle. Right? Change the relative orientation. You can keep the area the same, you can keep the vector field the same, but you could rotate it. Guess the other thing I always think about when I'm thinking about flux, you ever notice why they angle solar panels? Oh, happy spring, by the way. Sorry, I forgot about that. You ever see a solar panel and wonder why is it angled? I mean, like, I think the Dean's house has some solar panels on the roof just down Garrett Street. You ever notice why do they angle the solar panels? It's to make sure that the flux of sunlight is maximized. In other words, sunlight is coming in from, say, this direction. I want to take my solar panel and angle it so that it catches as much sunlight as possible. I want to take my solar panel and angle it so that the direction of sunlight compared to my solar panel is 0. The angle between the direction of my solar panel and sunlight is 0. That makes sure that I catch the most sunlight as possible. So laying it flat on the ground, sunlight will come in at some angle. That's not efficient. Well, it's more efficient if I angle it and then I catch more sunlight. Or imagine, I guess another way to think about it is imagine that you're lost in the desert and it starts raining. How do you want to hold your cup? I forgot my cup. I have a cup. I'm lost in the desert and it starts raining. How should I hold my cup? The rain direction I should, right? Right, rain's coming in this way. I want to make sure that my cup is going facing up so that cosine is maximized. And that way I catch as much rain as possible. If I hold it like this, I'm no bueno. Right, rain comes in this way. I'm holding my cup this way. No rain. No, rain on me. Make it rain. No. Okay. So there's three ways that we can change the flux. We can change the strength of the magnetic field. We can change the area of the loop, or we could change the relative orientation between the area and the magnetic field. So going back to the falling magnet, for example, which of those three am I actually changing as I let go of this magnet? Curious. Does the area of the loop change? Does the orientation between the magnet and the loop change? Now, what am I changing then? I'm changing the magnetic field strength. Imagine for a second, this little spot right there. We'll make a little loop. Imagine that little piece of the bar, of the pole, or the pipe. There we go. Imagine that little piece. As I drop this magnet in and it starts falling, right here at that location, what happens to the magnetic field strength as the bar magnet falls? It increases, right? The bar magnet gets closer to that little loop. It must increase. As it's falling, it's increasing. Of course, then when I get here and I pass it, and it starts moving away, what happens then? Just out of curiosity.
It's constant.
Yeah, is it constant as the bar magnet moves away? As it moves towards, it's increasing. So as it moves away, what would you expect? It's decreasing. Yeah. We'll have to keep going. Oh, but incidentally, notice that as it's moving towards, it's increasing with the North Pole facing it. As it moves away, it's decreasing with the South Pole facing it. For example, let's call the down one the North Pole and the up one the South Pole. So that also plays a role. So it's increasing with the North Pole, and then when it passes, now it's decreasing with the South Pole. Questions so far? Incidentally, it's not by accident that I use the term induce. Faraday's law is sometimes known as magnetic induction. It's the inducing of a current due to a magnetic field. And I don't remember what's on my next slide. Excuse me. Oh yeah, negative sign. Okay, gotcha. Yes?
Would there be a point where you drop the magnet in that pipe that the magnetic field has to remain constant, or else like it would slow down the magnet and then produce less current, so it would fall faster?
Yeah, let's see here. No, it will go to a point where the net force is 0, but it will not go to a point where the net force is opposite or in the direction that it's falling. There we go. Yeah, so what happens if you think the gravitational force stays the same, constant, whereas as the magnet falls, the force of the induced magnetic field on the magnet will continually grow. And the issue is that when they're exactly the same, the acceleration is 0, and then the force of the magnetic field stops growing. Yeah. I don't know if that answered it or not, but.
Yeah,
Okay.
there wouldn't be a point, like if you have a long enough pipe that it will like slow down and then just stop.
No. Just like the coffee filters, it doesn't matter from how high you drop the coffee filters, they'll never stop and change direction and start going up. They'll fall and they'll accelerate until they fall at a constant rate, but they'll never stop and change direction and start going up again. Yeah. So it's the exact same idea in that sense. And it comes down to the fact that the force of the magnetic field on the falling magnet is proportional to the speed of the magnet. Just like the force of air resistance on the coffee filters is proportional to the speed of the coffee filters, or speed squared, or whatever the exponent was, but it has a term that involves speed. So yes, that's why. Yep, and that should happen in general. If you have a force that depends on the speed of the object, then you'll hit some point of terminal velocity. You know what? I will amend my previous statement and say if I drop a magnet, okay, if I threw a magnet, then yes, it might slow down, right? So if I throw the magnet down faster than its terminal velocity, then it will de-accelerate until it hits terminal velocity and then everything's good. Same thing, if I throw a coffee filter down really fast, then it will de-accelerate until it hits terminal velocity and then it'll fall out. Yeah, okay. So I'll amend my statement slightly, but the same idea holds. Yeah, good. Other questions? You get some really wonky stuff going here. Okay, so Faraday's law, I gave you Faraday's law, just kind of like straight out definition. Here's what it is. And I should say also, this is empirical, right? Faraday, again, had nothing on, no underlying theory to go off of. You go into the lab, you notice, hey, wait a minute, the little ammeter needle changes. Can I measure that somehow? Can I get an idea about, oh, if I do it faster, the change is larger. If I do it slow, it's smaller. Oh, if I use more magnets and a larger magnetic field, I get a larger change. You know, like you go through and so it's empirical again. Where did he come up with this from? Patience. It's essentially what it is. Right? Just like how Fleming finds penicillin. Right? Alexander Fleming, discovery of penicillin. You know how he found it, right? I'm sorry?
Red mold?
Red mold? Yeah. I don't know if okay, if you say it was red mold, I'll believe you.
I said bread mold.
Oh, bread. Okay, even better. But if you say bread mold, I'll believe you. Yeah. In recollection, washed his glassware, went off to vacation, didn't wash his glassware very well, so he came back and there was mold growing on the glassware, except in a certain spot where the mold wasn't growing. He said, well, that's weird. Maybe it was bacteria. I can't remember. Something like that. He said, well, that's weird. There's a spot where the mold didn't grow. Maybe I should look at that. Maybe it was bacteria and that was where the mold was. Or I don't know, you know, something like that. He didn't wash his glassware very well. Wash your glassware. I think he said chance favors the prepared mind. You gotta be patient, and then you notice something interesting, and then you gotta examine it. Okay. So Faraday's law is this whole rigmarole. I've told you what EMF is. I've given you a mathematical definition of flux. And so the interesting thing you notice, we have to look at how the change in flux, right? It's not what the flux is, it's how the flux changes that's important. Now we come to the negative sign. That negative sign is sometimes known as Lenz's law. I don't know why, but Lenz's, for some reason within Faraday's law, this negative sign gets its own name, called Lenz's law. And the easiest way to think about this is if the flux is increasing, no, excuse me. The easiest way to think about this is that the induced current always opposes the changing flux. Or a different way to think about it, the huge one is, nature abhors a change. The current will run in your pipe to oppose the change in flux. So let's think about this. If the north pole of the magnet is going towards my loop, I have more and more magnetic field pointing down. Right, as the north pole falls towards that black segment of my loop, I have more and more field pointing down. So current will run in the loop to oppose that change. In other words, current will run in this copper pipe to generate a magnetic field pointing in which direction? Up. As the magnet falls, there are more and more magnetic field lines pointing down. Or maybe you should say the strength of the field pointing down gets larger. Nature abhors a change. It doesn't like that. So it will run current in the pipe to try to oppose that change. So if the strength increases going down, it will run current so that there is an induced field pointing up. Which way does the current run around the pipe? If you want to generate a current going up, which way, if you want to generate a field going up, which way should the current be running in the pipe? Curious about that. I owe you 5 minutes, don't I? Will you say yeah? Okay, let's start there Wednesday. Yeah. Chew on that. As the magnetic field goes down, as the more field lines going down, think about which way does current run in the pipe. Yeah. Use your right hand rule, chew that over, take your 5 minutes, go and do something useful with it. Like frolic in the sun. I'll see you Wednesday. Well, you guys look, what's wrong? Well, we can stay here and keep going. No, okay. Yeah, chew that over. I know that's a lot for the day. I know it's a lot, so. Yeah, chew it over, we'll pick up there on Wednesday. Yeah. You guys don't look happy. I'm like, here's your 5 minutes. You're happy? Okay. 'Cause I'm happy. The Elaine dance? No? The Elaine dance? Yeah. Oh, okay.